Now that we've got our part files prepared as DXFs, we're going to take a look at a slightly different scenario for exporting our SOLIDWORKS parts for laser cutting. When you laser cut a part, the laser cutter will outline a part with a cut, and then the part will drop out of the sheet of wood that you were cutting from. For the next part, it will do the same thing, much like cutting cookies out of a sheet of dough. Except we can't ball up the leftover wood or plastic from the cutouts, roll it back out into a sheet, and cut more cookies. But what if we were able to make a single cut that formed the edge of two or more parts at the same time? We save laser cutting time and also save on wood because we wouldn't leave any gap between the adjacent parts. Therefore, no useless scrap created between the parts. This way of laser cutting still isn't as fast as a stamping die, but it does help lower time and material costs. The time savings earned by making the extra effort required to share lines whenever possible can make a huge difference in production. When Ron used to subcontract the laser cutting of his radio-controlled airplane kits, optimizing the cut paths to share cuts whenever possible reduced his unit cost from over $80 a unit to $45 a unit. That's a huge change to the bottom line on an item that retailed for $142. So, in a case like the jewelry box we designed in Lesson 3, we can save considerable time and wood by using this technique.
We created the separate DXF files in Lesson 2J, and what we normally do is we'll go into Design CAD 97 over on the other computer, and we will bring in the DXF files independently into one common file for editing. We will carefully arrange them and delete any redundant lines and stuff like that, all while working in 2 dimensions. We can also assign colors and layers to create a file that requires very little adjusting in the SOLIDWORKS laser software prior to being ready to cut on the laser cutter. Design CAD 97 works really well. Note that in December 2020, Design CAD 2020 was added to the lab computer and will be available to students when the Science Maker Lab is reopened for teaching. But when we don't have access to that program, we can still accomplish this process in SOLIDWORKS, though we still don't get as much control over the cutting as we do in Design CAD. We also sometimes wind up with some lines cutting twice on the laser and other unwanted effects when we use the SOLIDWORKS method to lay out our multi-part cut files.
This SOLIDWORKS method will work, and it will still give us a file that is faster and uses less wood than cutting the parts separately. It also saves us operator time by running all the parts needed as a batch, rather than having to repeat the step manually, loading up and setting the origin for multiple cut files. To make one of these layouts in SOLIDWORKS is a 2-step process. We'll start off by looking at the assembly we're cutting the parts for. So this is an assembly of the box. It is assembled just as it will be when it's fully done. This box is made out of 5 unique parts, with 2 each of the side and end upright walls of the box. To make our cut file, we're going to need to create different assembly with these same parts, but with them arranged all in one plane. Before we do that, we're going to lay out a frame the size of our cutting bed to make sure that our batch cut file will fit on the bed. If the sheet of material we have is smaller, we will lay out a frame the size of the sheet we have available to work with. So to do this, let's activate the front plane. We then activate Sketch and make a rectangular 900mm wide by 600mm tall. This represents the size of the bed on the laser cutter. We'll call this Sketch Laser Bed. If we want, we can extrude it into a 3D object to make positioning parts on it easier. So now when we make a file of a bunch of parts stuck together, we can make sure that the assembly fits within the available cutting area. Now we're going to assemble our parts to make the most efficient use of this space. We'll start with the side plate.
If it's not in the right orientation to sit flat on the rectangle we drew, and we don't have a surface to place it on, we can either mate it to the front plane or use the tool that pops up when placing a part to flip it onto the orthogonal axes. The reason it's good to start with this side plate is that it's got a straight line along the top. Once we've placed it, we're going to insert components and add the bottom plate. It's going to fit perfectly into the bottom of the side plate, but instead of being on a plane normal to the plane of the side plate, we can put it coplanar and it still fits perfectly due to the interlocking tabs having an identical height and depth. As usual for rectangular objects, we will position it with 3 face-to-face mates along the orthogonal axes. Make sure one of these 3 mates is between the large side surfaces so that the parts sit coplanar to one another. If we look straight down at the assembly, it looks like we're putting these together in 2D, but we're still really working in 3D, so all 3 mates are still needed. It turns out that it's pretty tricky to get our components where we want them in our 900 by 600 box. So we will delete and redraw this now. The reason we're drawing in the opposite way that we usually do is that the laser always starts with an origin in the upper right corner. So we draw a box to reflect that. So this would be 900 by 600. We will say yes, and we will name this laser bed. Okay, let's see if we can move this. Yeah, so we can move the box around. Okay, so that gives us what we were looking for earlier. Let's position it and get back to the assembly.
The next component we want to put in is going to be the other side plate. Okay, so that's the front, the back, and the bottom. This arrangement isn't really great here because we could make these two lines come together, so we only have to cut this part of the line once, but we'd cut the whole thing. That's kind of wasteful. So let's get in there and let's do some mating. We're going to mate this face to that face, except we're going to flip the mate alignment. That's fine. Okay, then we're going to mate this face to that face, and we're going to flip that mate alignment too. Okay, so now we're looking pretty good, and we can just mate this tab face to that tab face to control the left to right positioning. Now we've got these 3 parts assembled. If we were to print them separately, the laser would have to come along and cut this edge for the purple piece, and then it would have to come along again for the greenish piece. Laid out like this, it can just cut that line once to create that edge of both pieces at the same time. Okay, let's finish up.
Let's insert an end plate, side plate too. We could put it in the middle here and mate this bottom piece into here, except then we have to put the other end plate on the other side of the 3-plate stack, and that doesn't really make efficient use of this wood because it would leave us with odd shaped remnants. So what we'll do is we'll put one here and one here. It means that we will leave a gap between the 2 end plates, but this is still less wasteful than our other positioning options. We'll get that mated into position. Now let's bring in the other side plate to here. We can actually print it in either orientation, but I'm pretty fussy, so we're going to flip it around using flip mate alignment. Alright, that's good. Okay, we want the tab facing inward, so we've got a nice straight line along here. So we've kind of got the top corner of our 60 by 90 centimeter board filled in, and we've only got 2 more pieces to add. So we're going to insert components, and we're going to get the upper lid. It's the bigger of the 2. Note that the order of our 3 mates doesn't matter. Since lazy is good, generally if we've got a pair of mates that I need visible to me in a given view orientation, we'll pick them while they're visible rather than repositioning to pick another pair. This saves a few seconds, and this can add up over a lot of mates. We like the positioning now, so we'll say yes to the mates to lock them in.
Now we're down to one more component, which is the inner upper lid, the one that sits inside the walls of the box to keep the upper lid from sliding out of position. So now we could put this here, and that would create a little bit of a waist. We'd have this kind of T shape here, which we're probably not going to find a good use for. But if we turn it 90 degrees and we put it here, we're going to create a bit of a gap here and a bit of an L-shaped remnant. So we're going to put our part down here because then the piece that remains after we cut our parts, the remnant, is going to be much more usable shape. Okay, so we've got all of our pieces that we need to cut, and they're all in one big flat assembly. So this is nice because it means that we can start the laser cutter only once, and it will cut all these pieces for us.
Now we still have some disadvantages over doing this in Design CAD, and they have to do with how the laser cutter works. The laser cutter software decides which order it's going to cut which line in. So if it cuts in a really logical order, it can be reasonably efficient. But sometimes it will cut a bit, then go start somewhere else, then jump to another area, spending more time moving around without cutting. This will add to the program time, but doesn't get your work done for you. You want the laser to be cutting as much as possible. But the logic of the laser is that it will follow a particular cut segment from one node to the next, and then decide if it's going to carry on in that same place, or move to another node and start there. Each node is an opportunity for the laser to decide to scoot across and work somewhere else. To minimize this undesired effect, we can minimize the nodes. So each segment in our DXF has a beginning and end point, right? These are the nodes. Even if we have 3 straight lines in a row, collinear, RDWorks has 2 opportunities to decide to go cut somewhere else, rather than continuing along what looks to us like a single straight line cut. When we create our cut file in SOLIDWORKS, as we've done here, we have no control over the nodes at all. But if we were using DesignCAD to prepare the drawing for cutting, we could eliminate these 3 lines and replace them with a single line. This would eliminate the nodes and force RDWorks to cut the complete straight line all at once. A bunch of small time savings like that can add up to a significantly shorter file runtime, and these savings can be multiplied by the number of times you cut that same file. Like we said earlier, DesignCAD is the best tool for optimizing laser cutting.
So we no longer need our laser bed outline, so we'll just delete it. We already know that our cut file fits within the bed. Time to save our file. To let RDWorks read it, we want to save it as a DXF. So, if we go File, Save As, and we look for DXF, we're going to find that it's not available. We can export as an STL and a whole bunch of other file format stuff, but we cannot export an assembly as a DXF. We need to work around this. To do this, we need to first save this assembly as a part instead of an assembly. So even though we made it as an assembly, we can save it as a part, and that has an important distinction to it.
To get to this part, we need to go open the new part file we just made. Once we're sure it's saved okay, we'll close our assembly file. We'll go to File, Open, and we'll select Part in the File Type dropdown to make sure that we're only looking at parts. So here's our part. Laser cut layout, we'll open that. We do not want to proceed with feature recognition. We just want to take a look at this one big part. We don't want it to be separated into separate subparts. Okay, so we've got the part open. We've turned it so we're looking normal to the face we want to cut. We'll make sure image quality is at its maximum. Because the part is almost all straight lines, the only thing this is going to really affect is the resolution of these round holes. But this is still a good habit to get into for exporting DXF files.
Okay, one last check to make sure perspective isn't turned on. If it is, we're going to get a bunch of double lines at the edges. Right, we're good. Okay, so now we're going to File, Save As, and we're going to come down here, and this time we do have the option to export as DXF. So we'll select DXF and save. We'll get our DXF export tool as usual. We want the annotation view. Our preview lines look clean and crisp. No fuzzy looking double lines or lines that we need to remove. Save. So it is now ready for use within the RDWorks software that creates the instruction files for the laser cutter.
That's it for Lesson 2J, Appendix 1.